All right, so we're starting section 3.5, and this section is going to be pretty quick. It kind of diverges from what we were doing in the previous sections because now we're going back into limits. So this section focuses on limits at infinity. And when I think of limits at infinity, I sort of just think of horizontal asymptotes. And so from algebra class, previous algebra class, should have been taught what horizontal asymptote is. And so here's an example. I have f of x equal to 3x squared divided by x squared plus 1. So this is our function, and the graph is what's in green of the function. And as the graph extends forever to the right, it gets closer and closer to the red dashed line. And the red dashed line, it's a horizontal line. It's got the equation y equals 3. All right, so as the graph goes forever to the right, it gets closer and closer to that red dashed line. And similar to the left, as it goes forever to the left, it gets close to the red dashed line, y equals 3. And so y equals 3 is a horizontal asymptote. Now it won't cross that asymptote as x goes really, really big to positive infinity or to negative infinity. So what I just said in words can be summarized in notation as x, and then it has arrows infinity. So as x approaches infinity, it goes forever to the right. The f of x approaches 3. So that's the graph itself approaches the horizontal line, dashed line, y equals 3. Same thing, as x approaches negative infinity, f of x approaches 3. All right, so that's a limit because I'm talking about the behavior of the graph as x approaches some kind of thing or some value. In this case, it's infinity. I also wrote up a table, and these are just examples, some x values and the corresponding y values for this function. And so, for instance, we have 0, 0, that's just the origin. And I skipped a point. I should have put in net 1, 1.5. So here I have -1 and then 1.5. I skipped that on the right side. I should have had 1 and then 1.5. But you'll see there's this symmetry to the graph. To the right side is a mirror image of the graph to the left side. So there's that y-axis symmetry, which is why you see the y-coordinates of the points, like for -10 and -100, being the same values as the y-coordinates for +10 and +100. And if you notice for -100, that's getting more and more negative. The y-coordinates are getting closer and closer to 3. So for -100, it's 2.997. That's more negative than -10. Even at -10, it's 2.9703. Similar to the other side for 10, right? It's the same y-coordinate as -10, and then 100, same y-coordinate as -100. So this is just a table just reinforcing the idea that as x gets really big, positive infinity, or gets really big to negative infinity, the f of x values get closer and closer to 3. All right, so that's why I drew in yellow, x going to negative infinity, so it's going extending forever to the left, x going to positive infinity, extending forever to the right. That's why the y-coordinates have f of x arrow going to 3 as you get farther to the left, and then f of x going farther to 3 as you go farther to right. All right, so the same information is displayed as this graph. So the point is that this is a horizontal asymptote, and that's what a limit at infinity is. And so here's the definition from the textbook. The line y equals L is a horizontal asymptote, so I'm going to abbreviate as HA, of f of x when the infinite limit as x approaches negative infinity is equal to L, or the infinite limit as x approaches positive infinity is equal to L. That is the definition of the horizontal asymptote. Now we have it in relation to limits. So we've already learned horizontal asymptotes in algebra class. You might have not heard it been described in terms of limits. So now this is what it is in terms of limits. Here's the theorem 3.10, and in the next video we'll make use of this theorem. But it's just saying if you have a limit as x approaches infinity, and you have the variable x raised to some exponent, and that exponent's a positive rational number, and it's on the denominator. Up top could be any number. So if you have some number divided by x to the r, it's going to equal 0 as x gets really big. Same thing, just with as x gets really big, as far as gets more negative, it still approaches 0. So like for instance, if I had limit x goes to infinity, and let's say I had 4 over x cubed. So as x gets really big to positive infinity, this is going to equal 0. All right, and same thing if it was negative infinity. All right, so here's guidelines and the finding limits at positive or negative infinity of rational functions. And this is something that I wrote up for an algebra course. The only added thing now is that we have this part which says, in other words, limit x approaches positive or negative infinity. So you're going to have a rational function, f of x equals, and then ax to the n, and then plus some terms, and then divided by bx to the n plus some terms. You only focus on the leading terms for the numerator and denominator. All right, so focus on the leading terms. I like to call them the dominant terms. Because I like to think of the leading terms sort of dictate or influence the graph the most. And especially true as x gets really big. Now, if the exponent up top, which is the degree, so the degree of the numerator is less than the degree on the denominator, so degree of numerator less than degree of the denominator, you have y equals 0 as the horizontal asymptote. And that's the same as saying the infinite limit x approaches infinity or negative infinity of the function is equal to 0. So again, there's this equivalence in definition. Y equals 0 is horizontal asymptote. That means the infinite limit is 0, the same value as the horizontal asymptote. Now, if the degrees, so leading terms exponents, if they have the same exponents, same degrees, then you just take the ratio of the coefficients for the leading terms. And so you're going to have y equals a divided by b is the horizontal asymptote. So the degrees are the same. Then it's y equals a over b. Now if the degree in the numerator is more than the degree in the denominator, so I have is m is bigger than n, degree numerator, bigger than the degree in the denominator, then there's no horizontal asymptote. The limit of the function as x approaches infinity or negative infinity is unbounded by some finite value. So unbounded, so it could go to positive infinity or negative infinity. So that's an infinite limit that goes to infinity or negative infinity for this third case. And again, this is degree of numerator bigger than the degree of the denominator. And so I'll use MUM for numerator, bigger than degree of denominator. And I'll use say denominator DENOM. All right, so that's for case 3. If the degree up top is more than the degree on the bottom, there's no horizontal asymptote. All right, this is going to be crucial, these guidelines, because I will be using these in the examples in the next video. And that's pretty much all of the concepts. A lot of this is review from algebra. It's just making sense of horizontal asymptotes in terms of infinite limits. Now, just before I end the video, I have some examples of polynomial or rational functions. And the first one, I have f of x equals 3x minus 1 divided by 4x squared plus 2. Now, the degree in the numerator is 1, degree in the denominator is 2. So technically 3x, there's an exponent of 1 for the variable x. So I say degree numerator is 1, degree denominator is 2. So I have my m is 1 and my n is 2. So m is less than n. All right, so then that puts me in the first category, m less than n, then y equals 0 is the horizontal asymptote. Okay, so for the second one, you'll see that the exponents are the same degrees, 2 and 2. All right, so m is 2, n is 2. So it's the coefficient of the leading terms, 4 divided by 3. And then for this last case, you have the degree in the numerator is 3. And that's, they keep using the letter m for the degree in the numerator, so m equals 3. And the degree in the denominator is 1 because x is the same thing as x to the first power. All right, so this is a case where m is greater than n. So the degree in the numerator is more than the degree in the denominator. That's the third case, so there's no horizontal asymptote. All right, and so for like the first example, so like for this one, we would say limit, if x were to approach infinity of this, then it's going to be equal to 0, the same value as the horizontal asymptote. The second one, we'd say limit, say x approaches infinity, f of x is going to equal 4/3, the same value as the horizontal asymptote. This third one, we know there's no horizontal asymptote. There's no finite value that it's going to be bounded by. So it's either going to be approaching infinity or negative infinity. And we'll do examples in the next video of getting a conclusive result like this. So it's either infinity or negative infinity, depending on the function. So that's pretty much it for the concepts. And I actually did 3 examples, sort of just discussing what these limits are at infinity. And I like to think of them as just finding the horizontal asymptotes, if they do exist. All right, so next video is going to be examples.